So in this video we're going to be looking at combination circuits, which takes into account our knowledge of series and parallel circuits and makes them more complicated. So in series circuits we know that the currents are all the same everywhere and the voltages add up to the supplied voltage, so there's a voltage drop across the components. In parallel, however, we have the same voltage flowing through, but the currents break up and split. So if this was 5 amps, this might have 2.5 and this 2.5, and they join back together and they're 5 amps again. Now, in series, we just add the resistors together, but in parallel, we use that formula to calculate the resistance. It's actually less than you expect. So, we're going to look at analyzing combination circuits, which are made up of parallel and series. So here we have a couple parallel resistors, and series. So we can actually simplify and turn all these resistors into one total resistance. The way we would do that is treat these as parallel, work out the resistance, treat these as parallel, work out the resistance, and then add together the three sets. So let's just do that now. So in here, we're going to have our resistance as equal to 1 over 15 plus 1 over 10, and that's going to be equal to 1 over 15 plus 1 over 10 is 1 over 6. So the resistance is going to be equal to 6 ohms through here. Now, here obviously 2.5 ohms, we don't need to do anything, but across here, again, they're in parallel, so we're going to have to use our formula. So let's just call this B. It's going to be 1 over 20 plus 1 over 25. If you type that into your calculator, you're going to get not a nice fraction. So what we're going to do is we're going to turn it into a decimal, so you get 0.09. So what we need to do is we need to rearrange times both sides by RB, divide by the 0.09, and we'll get RB equals 1 divided by 0.09. So the resistance through there is 1 divided by 0.09, which is 11.11 ohms. And then finally we can find the total resistance, because now we know this as if it was a component by itself, and this, and then these three are all just in series with one another, so we can simply just add the resistances together. So we're going to have 6 here plus 2.5 plus 11.11, which will give us 6 plus 2.5 is 8.5 plus 11.11 is 19.61. So there's actually 19.61 ohms of resistance through this circuit when we add the parallel and series components together. So we're going to do 2 examples. They'll take a bit of work, but let's get through them. So for the following circuit, calculate the current through each resistor. Let's just label them. Let's give them letters A, B, and C, and the potential difference across each resistor. So we have here, they're in parallel with one another, and then this is in series with whatever this becomes. So we have a combination circuit. So for the following circuit, calculate the current through each resistor. Well, we know 12 volts. So 12 volts is going to go to this entire loop and this entire loop, okay? So there's going to be a voltage drop across here and a voltage drop across here. So the first thing we want to do is, and I'll break this up into parts in a test question. So we're going to want to find the resistance through the 3 ohm and 6 ohm. So that resistance, we'll call it total for now. That's going to be 1 over 3 plus 1 over 6. And 1/3 and 1/6 will be a half. So then total resistance through those 2 parallel resistors will be 2 ohms. So we have 2 ohms going through there, 2 ohms going through there. So what we can now do is we can work out the current, okay, and the potential difference. So there's a couple ways we can do this. Let's just do it. We know that there's 12 volts the whole way through. We want to calculate the current through here, and through here. Okay, so what we can do is first we're going to need to work out the voltage drop. Not necessarily. V equals IR. So if we want to calculate the current, we need voltage divided by resistance. And if we want to figure out the voltage, we've got current times resistance. So technically right now, we don't actually know what the voltage drop across here and here is, do we? We could work out the total, current, because we know the total voltage, and we know the total resistance. The total resistance is 2 ohms plus 2 ohms, so the total resistance is 4 ohms. So we can do 12 divided by 4. And we can work out that there's 3 amps of current. So there's 3 amps of current here, and that means coming in, there's 3 amps of current. Okay, so how does that help us? Well, we've got 3 amps of current, so we could work out the voltage drop across here. So we could work out the voltage drop across C, because it's going to be the current at C, which we just worked out, which is the total current, multiplied by the resistance through C, which is 2. So it's going to be 3 amps times by 2 ohms. So it's 6 volts. So there's going to be a voltage drop of 6 volts through this one, which means if there's 12 volts, there's also going to be 6 volts going through these 2 parallel resistors. And it makes sense. If this was 2 ohms and this is 2 ohms, well, then this voltage is going to split evenly, give it 6 and 6. So we know that there's going to be, so the voltage at C and the voltage at A is going to be 6 volts, because these are parallel components, so they're both going to get the 6 volts. Voltage at B is going to also be 6 volts. So we've got the voltages, we've got the current at C. We know that current at C is just going to be the total current. So we've also got the current at C, and that's just 3 amps. So now we can work out what the current running through here and here is, because so the current running through A is just simply going to be the voltage at A divided by the resistance at A. And we now know that there is 6 volts divided by 3 ohms. So there's going to be 2 amps of current running through resistor A, and for resistor B it's going to be 6 volts because it's parallel, so it's still going to get the 6 volts, and it's going to be divided by the 6 ohms, so it's only going to be 1 amp, which makes sense. So if there's 3 amps here, it's going to be 3 amps here, and it's going to split off into 2 amps and 1 amp, and they're going to rejoin again at 3 amps. So we've worked out the current and potential difference, current through each resistor and the potential difference across each resistor. Now in your test I'm going to split it up into multiple parts, so you're not going to have to do as much thinking as what I had to just go through then. It'll be split up into parts, so it's a lot more straightforward. We're just going to do this example now. So in this example we have an ammeter measuring the current, and it reads at 4 amps. Find the resistance R. So we want to find this. Okay, so we've got 3 resistors in parallel with one another, and we've got resistance here. So if we want to find this resistance here, we're going to need to find the total resistance. We could actually find that out. So V equals IR, so R equals V over I. So the total resistance is the total voltage over the total current. So it's going to be 12 divided by 4 amps, which is 3 ohms. So these all of these resistors are going to add up to 3 ohms. So if we figure out the resistance through the parallel ones, we can figure out the resistance through this one. So to find out the resistance through the parallel components, I'm just going to call it T. It's going to be 1 over 20 plus 1 over 4 plus 1 over 5. If you type that into your calculator, you'll get 1 over 20, 1 over 4, and 1 over 5. You'll get 1 over 2. So then the total resistance through those 3 parallel components is going to be 2 ohms. So we have 2 ohms going through here, and so therefore we can find R. R is simply going to be the total resistance, which was 3, take away the resistance through here, which was 2, so we're going to have 1 ohm left over. So the resistance here is going to be 1 ohm. That was part A. Part B, calculate the potential difference across the parallel circuit, or the parallel part of the circuit. So there's going to be a voltage drop, because now this is like in series. This and this are in series with one another, so there's going to be a voltage drop. So we could work out the voltage drop across here, and then what's left over will be there. Or it doesn't really matter. We can just work out the voltage drop across here, because it's going to be 2 ohms. So part B, voltage is equal to current times resistance. We know that it's going to be 4 amps of current coming in. So it's going to be 4 multiplied by its resistance of 2. So it's going to be 8 volts, which makes sense. So if there's 8 volts across here, there'll be 4 volts across here. Now calculate the current flowing through each resistor. So I is equal to V over R. We know that voltage across here, we just worked out the voltage drop is going to be 8. So let's just call them A, B, C. So current at A will be 8 over 20. 8 divided by 20 is 0.4 amps. The current at B will be 8, because they all get 8 volts. Will be 8 over 20. Oh, sorry, not 8. Sorry, 8 volts over 4, sorry, because it's 4 ohms with resistance. So it's 2 amps. And then finally the current through C will be the 8 volts supplied divided by the 5 ohms of resistance, which is 1.6. And these 3 should add up to 4, which they do. 2 plus 1.6 is 3.6, plus 0.4 is 4 amps. So there's 4 amps flowing through, and then they join back up, and then there's 4 amps flowing here. So that's how we analyze combination circuits when they're made up of series and parallel. In your test, I'm probably going to give you series and parallel, and if there's combination, I'll make it very scaffolded and set out and clear. I just want to quickly touch on fuses and circuit breakers. So obviously, electrical safety is very important. So resistance wires can become very hot over time, and this heat can lead to fires, combustion of materials, and can cause fires, houses to burn down. So there's a couple things. There are things called fuses, there are things called circuit breakers. So fuses is just a thin wire, and it's connected in a circuit, and if it gets too hot, basically the wire's going to melt, the circuit's going to break, and the current's going to stop flowing, and that's going to prevent things from overheating and causing fires. However, fuses, because they break, they actually need to be replaced. It's a bit annoying. In houses, more often, you have circuit breakers. So if you've ever seen your power box outside, you're going to see these circuit breakers. So what happens is, inside the circuit breaker, there's a little metallic strip, and when that heats up at high temperatures, it causes it to bend, and it breaks the circuit. When that metal cools down, reaches room temperature, it straightens out, and you're able to reset the switch, and therefore you don't need to replace any parts. So when it cools down, you're able to so when it heats up, it bends and it trips and it breaks the circuit. It's like a circuit breaker. And then once it's cooled down, it straightens again, and you're able to reset it and reset it. So have we got these combination circuits? Well, these ones are series, parallel, and then there's some combinations. And we'll chuck them up on day map. Cheers.